Have you ever looked at, say, a jet engine? Or maybe just a simple household fan? Or even, think about this, your own heart, and wondered what's really going on inside? That hidden power.
It's fascinating stuff.
It really is. Today, we're taking a deep dive into that world, the world of turbo machinery. And our mission here, as always, is to sift through some pretty complex material, pull out those vital nuggets of knowledge, and basically give you a shortcut to being really well informed on the topic.
Cutting through the noise.
Exactly. And get ready for some aha moments today, because you'll find out how these machines add energy to fluids or take it out, how they're like perfectly matched to whatever job they need to do, and even the physics behind how engineers can design a huge, massive pump, starting from just a tiny model.
The scaling is amazing.
It really is. So at its core, turbo machines are these fluid machines, right? They can continuously transfer energy either to or from a fluid using rotating blades.
That dynamic action is key.
And for today's deep dive, we're going to focus mainly on two big categories, pumps and turbines.
The energy givers and the energy takers.
Okay, let's unpack that right away. We hear pumps and turbines, often in the same breath. But I suspect their core function is fundamentally opposite. Can you clarify that? What's the essential difference?
Yeah, that's absolutely the best place to start. It really defines the whole field. A pump, its main job is to add energy to a fluid.
Okay.
Think of it like giving the fluid a push, you know? This usually means an increase in the fluid's pressure. Though it's important to note, it doesn't necessarily mean the fluid speeds up right across the pump itself.
Ah, okay.
Okay.
So pressure, not always speed.
Right. And then, on the flip side, you have a turbine. Its purpose is to extract energy from a fluid.
The opposite.
Exactly. Here, the fluid is giving its energy to the machine, and this leads to a decrease in the fluid's pressure. And again, similar to pumps, not necessarily a decrease in speed. So fundamentally, it just comes down to the direction of that energy transfer. Is it going into the fluid or out of it?
Okay, so it really is all about which way the energy is flowing. That makes perfect sense now.
Yeah.
And what's really cool is how these like basic ideas show up in so many different machines we use every day. I know you've got some surprising examples.
Oh, absolutely. Take gas pumps, for instance. We actually break that down further depending on what they do. A fan, that's a gas pump with a pretty low pressure rise, but it moves a lot of fluid, high flow rate.
Like my ceiling fan.
Exactly. Ceiling fans, house fans, even an airplane propeller moving huge amounts of air, just giving it a little push.
Gotcha.
Then you have a blower. This gives you a moderate to high pressure rise and usually moderate to high flow rates too. Think of the squirrel cage blower in your car's ventilation.
Right, the heater fan.
Or, you know, that leaf blower you might have. It's designed to push air with a bit more force.
Definitely more force, judging by the noise.
Yeah. And finally, there's the compressor. This one's designed for a really high pressure rise, but typically lower to moderate flow rates, like an air compressor for tools where you need that high pressure air stored up.
Okay, fan, blower, compressor. Makes sense.
Yeah.
And the surprising examples.
Well, think about the human heart. It's essentially a positive displacement pump, constantly moving blood.
Wow, okay.
Or a jet engine. But it's brilliant. It actually has both. It's got a pump section that's the compressor at the front squeezing the air.
Right.
And then a turbine section at the back, which extracts energy from the hot exhaust to actually drive that compressor.
That's incredible. The heart in a jet engine, same basic principles. So yeah, this stuff really is everywhere, sometimes quietly, sometimes not so quietly, doing really important work, keeping us cool, getting planes in the air.
Everything.
All right, let's dive deeper into pumps then, the energy givers.
Yeah.
How do engineers actually measure their performance? It feels like there's more to it than just, how much water comes out the end.
Oh, definitely. Engineers look at a few key things. First, there's volume flow rate, or what the industry often calls capacity. Simple enough, how much fluid moves through per unit time. Then there's net head, usually written as H. This is basically the useful energy the pump delivers to the fluid, but it's expressed as an equivalent column height of that fluid.
Even if it's not water.
Even if it's oil or something else, yeah.
Yeah.
It represents the total lift pressure, speed, height change from inlet to outlet. It's a really useful combined measure.
Gotcha.
Net head.
And finally, there's brake horsepower, or BHP. This is the actual mechanical power you have to feed into the pump's shaft to make it turn.
Right, the power plug, essentially.
Kind of, yeah.
Yeah.
And it's always higher than the water horsepower. The useful power actually delivered to the fluid because, well, nothing's perfect. You always have losses like friction inside the pump, leakage, stuff like that.
Okay, so you put more power in than you get useful work out. Makes sense.
Always. That's efficiency, or rather inefficiency.
Right. So all this data, capacity, head, power, it ends up on these things called pump performance curves. I've seen charts like that. They look pretty complex. What are we actually looking at there? Why are they so important? They are super important. Think of it as the pump's unique fingerprint. It tells you exactly how that specific pump will behave under different conditions.
Okay.
On one end of the curve, you have what's called free delivery. That's the absolute maximum flow rate the pump can push out when there's basically zero resistance, zero net head.
Like a hose just wide open.
Exactly. But at that point, the pump's efficiency is also zero because it's not really doing useful work against any load.
Oh, okay.
Then at the other extreme, you have the shutoff head. That's the maximum head or pressure the pump can generate when the flow rate is zero, like you've completely blocked the outlet.
Keep the hose shut.
Right. No flow, maximum pressure potential. But the really critical part of these curves is the operating point.
The sweet spot.
It is the sweet spot. It's not just some point on the graph. It's the only place where the pump will actually operate correctly within a specific system. It's where the pump's available net head, what it can provide at a given flow rate, perfectly matches the required net head of the whole piping system it's connected to.
So the pipes, the bends, the height it has to lift, all that creates the requirement.
Precisely. And finding that intersection, that operating point, is crucial. If you miss it, you might not get enough flow, or you might be forcing the pump to work way too hard, wasting energy, maybe even damaging it.
Wow, okay, so matching the pump to the system is everything.
Absolutely everything.
Which brings up something you touched on. It raises this question. Why would a pump that looks, less efficient on its curve sometimes actually be the better choice? That feels wrong somehow.
It does sound counterintuitive, right? But it's a really common engineering decision.
Yeah.
Let's say you're choosing an impeller size for a pump. A bigger impeller might have a higher maximum efficiency, maybe 85% efficient at its best point.
Okay, sounds good.
But what if your system only needs a flow rate and head that puts that big impeller way off its best point? Maybe it's only 60% efficient there. Now, maybe a smaller impeller's peak efficiency is only, say, 75%. But if that smaller impeller operates right at its peak efficiency point for your specific system's needs,
It could actually use less total power.
exactly, it could use less overall power because it's perfectly matched, even though its own maximum possible efficiency is lower. It's about system efficiency, matching the pump to the job, not just chasing the highest number on the pump spec sheet.
That's a really important distinction.
Yeah.
Okay, efficiency makes more sense now.
Right.
But beyond efficiency, you mentioned damage.
Mm.
There's this big problem engineers have to watch out for. Cavitation. I've heard that term. It sounds nasty. What is it?
It is nasty. Cavitation is basically the formation of tiny vapor bubbles inside the liquid. This usually happens on the suction side of the pump impeller, where the pressure can drop really low.
So the water boils,
Mm-hmm.
even if it's not hot.
Kind of, yeah. It's low pressure causing boiling, not high temperature. But the real damage happens when those bubbles move into areas of higher pressure inside the pump and violently collapse or implode. Yeah, they create these tiny, high-energy microjets and shock waves. People say it sounds like pumping gravel or marbles, and over time, these impacts physically eat away at the impeller material, causing pitting and serious damage.
Yikes. Okay, so how do you stop that?
You manage the pressure at the pump inlet very carefully using a parameter called net positive suction head, or NPSH.
Okay.
There are two sides to it. First, there's NPSH required, or NPSHR. That's the minimum pressure head the pump needs at its inlet to prevent cavitation. The manufacturer tells you this, and it usually goes up as the flow rate increases.
More flow, more NPSH needed.
Right. Then there's the actual NPSH, sometimes called NPSHA, which is the pressure head your system actually provides at the pump inlet. And here's the catch. The actual NPSH usually decreases as flow rate goes up, mainly due to friction losses in the suction pipe.
Ah, so they're moving in opposite directions as flow changes.
Exactly. And cavitation happens when your actual NPSH drops below the NPSH required by the pump, so you have to make sure you always have enough actual NPSH available.
And temperature plays a role too.
It does. Warmer water, for example, has a higher vapor pressure, meaning it boils or cavitates more easily at lower pressures. So higher temperatures reduce the actual NPSH available, meaning you might hit cavitation limits at a lower flow rate than you would with colder water.
Wow. Okay. Lots to consider just to avoid those little bubbles.
It's a major design constraint for pumps.
So we've got single pumps covered. But what if you need way more pressure or way more flow than one pump can give? Can you just hook a few together? Seems like that could get complicated.
It can, and you have to do it correctly. You can arrange pumps in series, one after the other, to get a higher total head, basically adding their pressure boosts together.
Stacking them up.
Yeah. Or you can put them in parallel, side by side, to get a higher total flow rate at the same head.
Okay.
But, and this is a big but, you have to be really careful, especially if you're using pumps that aren't identical, dissimilar pumps.
Why is that?
Well, put a small pump in series with a big one, and the big one might force so much flow through the small one that it goes beyond its maximum flow rate, maybe even acting like a restriction, a head loss.
So it actually hurts performance.
It could, yeah. Or in parallel, if one pump creates much more pressure than another at low flow, it could actually force flow backwards through the weaker pump.
Whoa, okay.
Which is obviously bad. So best practice is often to use identical pumps, especially in parallel. And you need things like check valves in parallel setups to prevent that backflow if one pump stops. You really have to analyze the combined performance curves carefully.
Right, it's not just plug and play.
Definitely not.
Okay, so to wrap up pumps, let's look inside. What's actually doing the work? What are the main ways pumps are built internally?
Good question. Broadly, there are two main categories based on how they work. First, you have positive displacement pumps.
Okay.
These don't use the continuously spinning blades like we've been talking about.
Yeah.
Instead, they trap a specific fixed volume of fluid and then physically push or displace it.
Like squeezing a tube.
Exactly. A peristaltic pump, like the ones used for IV drips or even like your esophagus moving food, works that way. Gear pumps, screw pumps are other examples. They trap fluid between teeth or threads and force it out.
And what are they good for?
They excel at high-pressure applications, handling thick, viscous fluids, and when you need really precise flow control, like metering chemicals.
Yeah.
A key thing is their net head, the pressure they generate, is pretty much constant regardless of the flow rate.
Interesting. Okay, so that's one type. What's the other?
The other big category is dynamic pumps. These are the ones that use rotating blades, called impellers, to continuously add energy to the fluid through dynamic action.
Ones we usually picture.
Probably.
Yeah.
And within dynamic pumps, there are three main flavors. First, centrifugal pumps or radial flow pumps. Fluid comes into the center, the eye of the impeller, actually axially.
Okay.
And then it gets flung outwards radially towards the casing by the spinning impeller blades. They usually have that characteristic spiral, snail-shaped casing called a scroll or volute.
I've seen those.
That scroll is important. It collects the high-speed fluid leaving the impeller and gradually slows it down, converting that speed energy into pressure energy efficiently. You find these everywhere. Dishwashers, washing machines, industrial water pumps. Even hair dryers, you mentioned. Some use centrifugal blowers, yeah. And engineers can actually do preliminary designs by looking closely at how the fluid flows relative to the blades, using things like velocity triangles and the Euler turbo machine equation to predict the energy transfer.
Cool. Okay, centrifugal. What else?
Then you have axial flow pumps. Here, the fluid enters and leaves along the axis of rotation, pretty much straight through.
Like a propeller.
Exactly like a propeller. The blades act like little airplane wings, generating lift that pushes the fluid along. Think boat propellers, the fan in your computer, big ventilation fans, high flow, low pressure rise, typically.
Got it. And the third?
Mixed flow pumps. As the name suggests, they're kind of an intermediate type. The impeller pushes the fluid both outwards radially and forwards axially. They sort of blend the characteristics of centrifugal and axial pumps.
Okay, so positive displacement and then dynamic. Centrifugal, axial, mixed flow. Quite the variety.
It allows engineers to pick the right tool for the job.
All right, let's flip the script now. Let's talk about turbines, the energy takers, the power generators.
Yes, the other side of the coin. And what's really interesting right off the bat is that turbines are generally more efficient than pumps.
Really? Why is that?
Couple of reasons. They often spin slower, which means less friction loss. But maybe more importantly, think about the pressure. In a pump, pressure is increasing as the fluid goes through, which is called an adverse pressure gradient.
It's fighting against the flow direction.
Right. And that makes the fluid boundary layers, the thin layers right next to the surfaces, more likely to separate, causing turbulence and losses. But in a turbine, pressure is dropping. That's a favorable pressure gradient.
It's going with the flow.
Exactly. So those boundary layers tend to stay attached better, leading to smoother flow and lower losses. It's inherently a more efficient process, sometimes over 95% for big hydro turbines.
Wow, 95%. That's impressive. So what kinds of turbines are there? Is it the same sort of variety as pumps?
Pretty similar categories, actually. You do have positive displacement turbines, but they're not really used for generating power. They're used for flow measurement.
Ah, like the water meter.
Exactly. Your home water meter, often with that wobbling, nutating disc inside, is a perfect example. It uses the fluid flow to turn a shaft, and the number of turns tells you how much volume has passed through. Very precise.
Okay. So what are the other power generating ones?
Those are the dynamic turbines, and they mainly fall into two types. First, impulse turbines. The classic example is the Pelton wheel.
I think I've seen pictures. Buckets on a wheel.
That's the one. You have a high-speed jet of water coming out of a nozzle that hits these specially shaped double buckets on the rim of the wheel.
Why a funny shape?
It's genius. The bucket splits the jet in two and turns each half almost 180 degrees backwards. This extracts nearly all the kinetic energy from the water jet, creating maximum impulse force to spin the wheel. For peak power, the bucket speed should be about half the jet speed.
Clever design. Okay, that's impulse. What's the other type?
The other main type is reaction turbines. These include the Francis turbine, which is sort of radial or mixed flow, and the propeller or Kaplan turbines, which are axial flow.
So they work differently from the Pelton wheel.
Yes, they operate completely full of water, submerged. They have fixed guide vanes called stay vanes, and then adjustable vanes called wicket gates.
Wicket gates.
Yeah.
Like on a fence.
Kind of. Think more like adjustable louvers. They control the angle and amount of water flowing onto the main rotating part, which is called the runner. The water pressure drops as it goes through the runner blades, pushing on them and making them spin.
Okay.
And a really critical part of reaction turbines, especially Francis and Kaplan, is the draft tube. It's this specially shaped expanding pipe at the turbine outlet.
What does that do?
It serves two purposes. It slows down the water leaving the runner, which recovers some of the leftover kinetic energy, converting it back into pressure energy, effectively increasing the pressure drop across the runner. And it allows the turbine to be placed above the final tailwater level without losing that part of the head.
So it helps squeeze out more energy.
Exactly. But designers have to be careful because the lower pressure in the draft tube can increase the risk of
Cavitation.
You got it. Same problem, different machine. And here's another subtle detail. Engineers look at the swirl of the water leaving the runner. Ideally, you don't want too much swirl, as that's wasted energy. But for many hydroturbines, the absolute peak efficiency happens with a tiny amount of swirl in the same direction as the runner's rotation with rotation swirl.
Huh. Not zero swirl, but just a little bit in the right direction.
It's one of those optimization errors that shows how complex these systems are.
Definitely. Now, thinking about visible turbines, the ones we see most often these days are probably wind turbines.
Absolutely. And typically, we're talking about horizontal axis wind turbines, HIWTs, because they tend to be the most efficient for large-scale power generation.
The big ones with 3 blades, usually.
Usually 3, yeah. And every wind turbine design has a power performance curve. It shows how much power it generates at different wind speeds.
Okay.
There's a cut in speed, the minimum wind speed, where it starts making any useful power at all.
Makes sense.
Then there's the rated speed. That's the wind speed, where it reaches its maximum designed power output. The generator is maxed out. And finally, there's a cutout speed. If the wind gets too strong, the turbine shuts down and feathers its blades to prevent damage from extreme forces.
Safety first.
Always. And here's something really important about wind power. The available power in the wind is proportional to the cube of the wind speed.
The cube. So double the wind speed.
8 times the available power.
Whoa.
Yeah, it's huge. And it's also proportional to the square of the blade diameter. Double the diameter, you sweep 4 times the area, so you get 4 times the available power.
Okay, that explains why they keep building them bigger and bigger.
Exactly. Small increases in size yield big power gains. But there's a limit. A fundamental physical limit called the Betz limit.
Betz limit.
Yeah, named after Albert Betz. It's the absolute theoretical maximum fraction of the wind's kinetic energy that any wind turbine, no matter how perfectly designed, can ever capture. And that limit is about 59.3%, or mathematically 16/27.
So you can never get 100% of the wind's energy.
Never, because if you stop the air completely, it would just pile up and flow around the turbine, not through it. The Betz limit occurs when the wind speed passing through the turbine blades slows down to exactly 1/3 of the original upstream wind speed. That's the sweet spot for maximum energy extraction.
Fascinating. A hard physical limit.
Yep. Physics always wins.
So taking all this theory, performance curves, limits, different types,
Yeah.
how do engineers actually use this to build these things? Going from a concept, or maybe a small test model, to a giant power plant turbine seems like a huge leap.
It is a leap, but it's a leap made possible by some really powerful engineering tools, mainly dimensional analysis and what we call affinity laws.
Okay, tell me about those.
Dimensional analysis lets us group variables into meaningful dimensionless parameters. For pumps, we get things like the head coefficient, the capacity coefficient, the power coefficient. These numbers basically describe the pump's performance in a universal way, independent of its size or speed, or even the fluid it's pumping. They capture the shape of its performance curve.
Like a universal fingerprint again.
Exactly. Then the affinity laws build on that. They are scaling rules that let engineers predict the performance of a new, different size pump or turbine, let's call it pump B, as long as it's geometrically similar to an existing one, pump A, that they've already tested, maybe as a small model.
Geometrically similar, meaning scaled up or down perfectly.
Precisely. Same shape, different size. These laws tell you how the head, flow rate, and power will change if you change the size or change the rotational speed or even use a different fluid. It's incredibly powerful for design.
That's the part that always gets me modeling a huge hydro turbine with something small in a lab. And I know there's a handy mnemonic engineers use for how performance scales just by changing speed. Very hard problems are as easy as 1, 2, 3.
Yes, that's a great one. Very hard problems stands for V dot, volume flow rate, H head, and P, bhp brake horsepower. And the 1, 2, 3 tells you the power they scale with related to rotational speed N.
Okay,
So for a given pump, if you change its speed, the volume flow rate, V dot, changes proportionally to speed to the power of 1. The head H changes with speed squared, N left. And the brake horsepower, bhp, needed changes with speed cubed, N.
speed cubed for power.
Yes. So if you double the pump speed, N times 2, the flow doubles, 2 datas, the head quadruples, 2 and then 2 with 4, and the power required goes up by a factor of 8. 2 and up is 8.
Wow. That's why just speeding things up gets expensive fast, like that water tunnel example you mentioned.
Exactly. Doubling the speed costs 8 times the power, roughly. The affinity laws make those consequences really clear.
Okay, that's incredibly useful for scaling. But how do engineers choose the right type of pump or turbine to begin with? Centrifugal, axial, Belton, Francis. There are so many choices.
That's where another dimensionless parameter comes in, called specific speed. Think of it as classifying the pump or turbine based on its optimal operating conditions, high head-low flow, low head-high flow, or somewhere in between.
So it guides the initial selection.
Exactly. For pumps, we calculate the pump-specific speed, NSP. It's calculated using the speed, flow rate, and head at the pump's best efficiency point. A low NSP value, say below 1.5 roughly, tells you a centrifugal pump. High head, low flow is probably the best fit.
Okay.
A medium NSP, maybe 1.5 to 3.5, suggests a mixed flow pump. And a high NSP above 3.5 points towards an axial flow pump, low head, high flow. It's a great starting point for design. Interestingly, fluid properties like density don't directly show up in the NSP calculation itself, but they definitely affect the power needed.
Right, and turbines have something similar.
They do. Turbine-specific speed, NS, it's defined a bit differently, using power output instead of flow rate, but serves the same purpose. A low NST indicates an impulse turbine, like a Pelton wheel, is best typically for very high head situations.
Okay.
Mid-range NST points to Francis turbines, and a high NST suggests Kaplan or propeller turbines for lower head, high flow applications like run-of-the-river hydro.
So specific speed is like a matchmaker for the application and the machine type.
That's a great way to put it. And just one more fascinating type to mention, pump turbines.
They do both.
They do. It's a single machine, usually based on a Francis design, that can operate efficiently as a pump and as a turbine just by reversing the flow direction and rotation. They're used in pumped hydro storage, pump water uphill when electricity is cheap, then let it flow back down through the same machine acting as a turbine and generate power when demand is high.
Incredible flexibility. Slightly less efficient, maybe?
Slightly less efficient than a dedicated pump or turbine, yes, but the flexibility is often worth it.
Wow. What a journey through turbo machinery. Seriously, from like the almost invisible compressor in my fridge to those enormous wind turbines dotting the landscape. These machines are just incredible feats of engineering, so precisely designed for what they do.
They really are. That interplay between the fluid, the energy transfer, the detailed design, it's quite something. And understanding those core ideas, head, capacity, efficiency, and especially how things scale with size and speed, it really unlocks how these complex systems work.
It definitely makes you look at things differently. So think about this. Now that we've unpacked all this, what's one turbo machine you encounter regularly that you might see in a totally new light? And what question does all this spark for you, for maybe digging deeper later on?
Good questions to ponder.
Maybe, just maybe, it's time to go give that noisy leaf blower a little nod of appreciation. It is a blower after all, doing its specific job.